Okay, here we'll talk about some examples from lecture 1 and 2 about stationary wave and on waves with strings. You can pause the video and find the question. We'll start with May, June 15, paper 2-3. Alright, let's read the question. You have two overlapping waves with the same type traveling in the same direction. The variation with distance x is shown. Speed of the wave is given, and the waves are coherent and produce an interference pattern. So I want to address coherence and interference first. This one, I will talk about it later in the second half of this chapter, after your semester exam probably. Okay. We're going to move on to part 2. Okay, I select this question because I want to do part 4 with you. Okay, so part 2, determine the frequency. We can look for lambda. 3.2 is pretty obvious. If not, you can take 0.8 and 4 minus 0.8, which is 3.2. Okay, and then you can use the equation V equal to F lambda. Substituting 3.2 in. Wave speed is 240 meter per second. Okay. This will give you 75 hertz. Okay. Part 3, state the phase difference. So when they say state means you should be able to see immediately lah, and it has to be in degree. So I don't know whether you can tell, these two are 90 degree apart, sine and cosine curve. Okay, but if you have problem, you can always take two separate points, equivalent points to compare. Let's say you want to compare these 2 points because it's easier. I tend to compare these kind of points because they are on the x-axis. Okay, so the separation between those 2 points is 0.8 meter. So if 3.2 meter is 360, 0.8 should be 90 degree. Okay, and part 4, use the principle of superposition to sketch the resultant wave. So just for posterity and working, I will write down the working on how I got 90. Okay, just divide by 4 lah, 360. Alright, now we're going to do the difficult work of sketching the total or the resultant of these two waves due to superposition. Okay, but it's easy to do. 0 plus 2 is 2 on one side near the x-axis, and 0 plus 2 is 2 on the other side. Okay, we can also tell that 1.5 plus 1.5 is 3. Negative 3, sorry. Okay, so here you can also, when I tend to find one place where one graph is 0 and then take the other point as the total. 0 is my favorite number, guys. Easy ma. Alright, so where were we? You can see I created another total on the upper right side. Okay. And right now, I'm also creating a total on the upper left side. 1.5 plus 1.5 is 3. So I can roughly see the shape now, and I know definitely it will cross the x-axis somewhere here, and I have to be careful about where it crosses. So I'm going to take a point where they both cancel out, and actually coincidentally, or maybe not, it's actually positive 1.5 on one side and negative 1.5 on the other side. So this is where it will be 0. So the same thing will be mirrored on the right side. Find the place where it's positive 1.5, and you will find that underneath is negative 1.5. Generally, if it's the real class, I would suggest you use a ruler to run it through your paper lah. Okay, so now we join them with a smooth and steady hand, guys. Smooth and steady hand. Okay. By the way, there's another point that I didn't plot, which is about 1.6. So at 1.6, the other graph is 0. It should cut. There you go. Okay. And I'm going to join them with a smooth hand. And you might be asking me, how strict is the examiner? Well, this kind of thing I don't know. But I am quite strict lah. Like, I'm particular about the shape. If it's not clear by now that I'm particular about how I sketch my graph, were you watching my lectures? Alright, so anyway, you can see the red graph is the total of the black graph. Anyway, if you're wondering why my mouse is hovering around, I'm actually opening Chrome to look at the mark scheme to tell you where the marks are. Alright, and the marks will disappear for a while. 1 mark for 3 plus minus 3 meter as amplitude, and 1 mark is the correct shape. Now the shape correct or not is the examiner's judgment. So try to be as exact as you can within reasonable time. Don't spend 20 minutes sketching one graph lah. Alright, next question. Ta-da! May, June 17, paper 2-1. Question 4. Right, so state the conditions required for the formation of stationary waves. This one is in your notes lah. So just repeating it to help us remember. We need two waves, okay? Two identical waves. They should have the same frequency, wavelength, and amplitude. Have to have the same amplitude lah. If not, they cannot cancel. Okay, we need the cancelling as well. So, two waves with the same frequency, wavelength. Actually, when you say the frequency and wavelength is the same, naturally the speed will be the same already, okay? So two waves with the same frequency, wavelengths, and amplitudes. Ta-da! One mark. Second mark, they overlap and they are traveling in the opposite direction. If they overlap and they travel in the same direction, you will just consistently get 2A all the way. Okay, overlaps while traveling in the opposite direction. Okay. Right, so now you see this is the standard one with a string and a vibrator. Okay, it's stretched by passing the other end through the pulley. So let's go back to our guitar. Now, if you have a guitar, hang on, past me is highlighting the keywords that I have already mentioned. I speak too fast, although I already speed up twice. This video is twice the speed of the recording. Anywho, I want to talk a little bit about the string. When you play guitar or any string instrument, you notice that we adjust the tension a lot because that is very important. The tension on the string, which is changed in this case by the load. So this load is to vary or adjust the tension. Like on your fretboard of your guitar, you adjust the knobs. Okay, so when we change the tension, what we change is actually the speed of the wave. So the speed of the wave, when tension increase, the wave will travel faster. Depends on two things, the tension and the mass per unit length. Not in your syllabus, but makes sense, right? Thicker string, deeper sound. Okay, so anyway, we're going to read the question. Frequency of vibration is 250. Transverse wave travel on the string with the speed 12. Wave is reflected at the pulley. You get a standard stationary wave between points A and B at t equal to t1. So, out of habit, just want to label the notes lah. Not necessary, didn't ask for it in this question. Just want to do it. So, calculate the distance AB. I see that AB is actually 3 node to node. So 3 lambda over 2. Okay, 1.5 cycle. And at this point, I notice, oh boy, I need to probably find lambda. But I have enough information. We have the speed of the wave, 12. And we are also given the frequency, 250 Hertz. So to find lambda would be a piece of cake. And once we have lambda, right, we can substitute into the equation AB is 3 lambda over 2. Alright, so hang on while I clicky the calculator. There you go, 0.048 meter. And I will just find AB now, easily 3 over 2 times 0.048. That would give me 0.072, I think. Okay, so note that the wave that they drew for you just now is at t equal to t1. Now they want you to draw 2 milliseconds after that and 5 milliseconds after that. Well, first order of business, I need to know what the period is, meaning how many cycles is 2 and 5 milliseconds. So by calculating the period, I will find that this is 4 milliseconds. Okay, 0.004. So this is 4 milliseconds, which means 2 milliseconds is half a cycle. Okay, so I'm going to go back to the diagram now and think about how do we draw half a cycle after this. Okay, so if the particle, let's say we take the antinode lah. If the particle go down, and come up again. That is one cycle. So half a cycle, don't come up though. You just go down and stay down. Alright? Which means you kind of like expect A to be at the lowest position. So we're going to draw that. You will get this wave shape. Okay, I'm just trying to plot it so that it looks symmetrical, I guess. Okay, symmetrical. It should also have the same amplitude as the neighbor. Okay, on paper it should be easier because you have a ruler. I do not have a ruler on OneNote. I don't know why. Okay, anyway. The same thing for the other side. And the middle node to node antinode should go up. So I'm just going to sketch the wave. Okay. So quite nice one. You draw nice little diagrams like this. You get marks. Isn't that nice? Do not forget to label your line. Okay. So try to make it as symmetrical as you can. There you go. Let's label this. This is line P. Yep. Okay, next one. 5 milliseconds. So 4 milliseconds is one cycle. So it's 4 plus 1 millisecond. So 4 plus 1 means 1 millisecond because one cycle don't count already, right? Think about trigo. Okay, so this is 1/4 cycle. So we just got to half the A. The A doesn't go all the way down, it just travels to the middle. Okay, so here to here is half. There to there is 1. So here is 1t. If you have add another quarter to get 5/4t, you will arrive at this point. Alright, so the particle go down, come up, center. So I'm just going to rub all of that off. That was just to explain to you. And I will now draw line Q. How would line Q look like? If I'm that kind of teacher, I'll like, let's draw together. You'll be doing work anyway. So yeah. As you can see, I care about this stuff. Draw a nice straight line Q. Alright. I don't know whether you noticed, paper 2 is actually quite easy compared to paper 1. So I shall do some paper 1 questions shortly after this. Ta-da! So I'm doing these questions. Try to find them. You can also find them in the handouts. Alright, so in this case, you have a vibrator, a string. You should be used to this setup by now. You get a series of stationary wave when you add to the frequency of the vibrator. I discussed this in lecture 2. Okay, so let's say I label this NN. This is the simplest form. Ta-da! And this would be L is lambda over 2, so lambda is 2L over 1. And you notice that immediately you can cross out C and D, the beauty of objectives. Alright, the next one, we'll have a node stuck in the middle. You get something like this. Dun, 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 dun. And in this case, lambda is still equal to L, or 2L over 2. So answer is A lor. You can continue but it's objective. Next question. Now this is a little bit more complicated. Diagram shows a stationary wave at times t that's been set up on a string. Now it has both fixed ends, so there's a node and node each side. Okay. The nodes of the stationary wave occurs at PQRS. So there are actually 4 nodes. Point X is moving down at time t equals 0. Sure. The point on the string vibrate with time period t and the maximum amplitude of 2 cm. These are all important information. Okay. Which graph shows the displacement of point Y? So we are looking at point Y. Okay, not X but Y. I'm just going to draw the wave first to give us a better idea. Okay, and also label the antinodes. So there will be an antinode here, antinode here, antinode here. There you go. See, it must be nice. The shape have to be nice. Okay, anyway, this is the antinode. And if you think about it, if X is on the way down, Y should also be on the way down because everything between P and Q and R and S are in phase. So which one is traveling down? C and D, throw away. All right. Next, do you think Y have maximum amplitude? No law. Y is not at the antinode. So because it's not at the antinode, the maximum displacement will be less than 2, less than the maximum amplitude. So you get A. Now, here's a bonus. Identify the MCQ options B, C, and D on your string. Okay, I think B is pretty obvious. B would be the antinode between RS or the antinode between PQ. Remember, RS is a photocopy of PQ. Okay, and A is point Y, but it can also be this point. This is the mirror twin. Okay, and you might be thinking, hang on, if P and Q is also a photocopy of this, then there are also two A's here. Okay, so there are 4 possible options for graph A. Okay, let's move on. What about graph C and graph D? Well, graph D is the most straightforward because D also have 2 cm, so D would be the antinode that is traveling in the opposite direction. So this is D. And if you want to find C, this is C, where it's like the anti-A. Okay, so if you got all of this right, all the options are circled in circles. If you got all of this right, it means that you already understand how a stationary wave pattern looks like. Okay, as in you can visualize it, which means the next question should be easy peasy. Okay, which row describes the oscillation of 2 moving particles in a stationary wave that are separated by half a wavelength? You might be thinking, nah, half a wavelength, but must it be like this? No, there's no such thing that it must be between 2 ends, because if you think about it, the lambda over 2 can be any point. Let's say I take antinode to antinode, also lambda over 2. I take any point in between here, also lambda over 2. So IDK. But the phase difference only have 2 options. If they move together and they're in phase, 0. If they move against each other, like the one next door and the one next door, the one is total opposite, 180 degrees. So 90 degrees, you just throw away. Okay, not possible. So if it's 180 degrees, it can be the blue one, definitely not the orange one, or it can be some random one like this. Okay, and then if you think about the sine graph and the cosine graph, like I draw just now, there you can see here. See now, 180 degree, it should be the same. All right, but if you're struggling with why the amplitude is the same, I'm just gonna do some trigo with you lah. Okay, simple trigo. Okay, I'm gonna disappear for a while so you can see my drawing. There. All right, so you can see I've already drawn the wavefront. It looks like a sine curve as usual because we are easy and more familiar with sine. So let's consider, I don't know any random angle . Okay, if you really understand the unit circle, all of this will make a lot of sense. True story. Think about it for a bit. Like, why do I say that the amplitude is the same as long as they're 180 degrees apart? What do you understand about the idea of base angles? Okay, it can be any point here and here also can. Okay, amplitude means magnitude. Okay, anyway, let's do some trigo. Okay, let's say we take a familiar angle, the green one, 30, sine 30. Okay, I have no idea what. Okay, there we go. Let's say we take sine 30. And just the magnitude, because amplitude is magnitude, we just consider plus minus. So sine 30 will be equal to sine 180 minus 30, and sine 180 plus 30, and sine 360 minus 30. Okay, so the magnitudes are all the same. So all of these points will have the same amplitude. They just are at that same amplitude at a different time. You see, so the first 2 points will be at the same amplitude at different time, but their separation is 180 what? Alright, sine 30 and sine 180 plus 30, the separation is 180. And then the other one, the separation also 180. And I've run out of video, so you can go back and look at the video again. Alright, I will see you in class. You are done. Good job. Go do the task. I'll see you then.